Hello and welcome. This is going to be our lecture video for December 12th. Let's get started with a quick little do now. Describe or draw a picture of how a single, double, or triple zero appears in the graph of a polynomial. So I'm going to draw my x-axis. Because a zero is specifically when the y value is 0 and we're crossing the x-axis. So that x. Here's my y-axis. A single zero just crosses the x-axis. It doesn't do anything special at the x-axis. It's just following some trajectory and just happens to cross. Double zero is turning right when it hits the x-axis. So it touches the x-axis, but then goes through. This is a double zero. Triple zero puts an inflection point right on the x-axis. So it lies flat to the x-axis for a second, kind of like a double zero, but then instead of bouncing, it does break through. And this can kind of look like a single zero, except for there's a little wave in here that allows the function to lie flat for just a moment as it touches the x-axis. We can keep going. A quadruple zero would then look a lot like a double zero. They tend to just be a lot wider, and it looks like it's lying flat for longer along the x-axis. A zero with a multiplicity of 5 would look kind of like a triple zero, but just stretched out. And I encourage you to play around with this in your calculator. Just create y equals equations that have repeated factors in them, and you can have as many multiplicities at a value as you want. Goal for today is to be able to use complex numbers in mathematical operations, simplify complex answers, factor by grouping, and interpret imaginary roots. Why are we doing this? So we can continue to do math even if a polynomial has imaginary roots. All right, how do we add complex numbers? So here's what I have to say about adding complex numbers. It is just like combining like terms. All right, the parentheses aren't really even needed here, except for they're kind of keeping the complex numbers together. We can drop those parentheses, and just the 4 and the 5 combine to be a 9. The 3i and the negative 2i become a minus I. And there you go. That is your final answer. This is said to be just a single complex number containing a real and an imaginary part. Try and convince yourself to think of this as just one number here. The one maybe ever so slight difference between combining complex numbers and adding like terms is we put our imaginary unit at the end, while typically we bring variables to the front. So just a slight change there, but not a big one. And okay, we're going to do more operations with complex numbers, but I'm going to show you how to do this in the calculator now too. You do have to change a specific mode on your calculator. Let me open this up. All right, so there is an imaginary number on your calculator, and it's actually been on the front of your calculator all along. It's that little I right down there by your decimal point. So you can reach it by doing second decimal point. If you try that right now, it might not work though, because you need to make sure you're on a specific mode. So press mode, and what we want is this a plus bi. That lets us be in complex number mode. And you can just leave your calculator on this. There's really no reason to not be on complex number mode. It doesn't change any of the other math, but now it just when the answer is imaginary, it will display it versus giving you a non-real answer error. Okay, so let's do this next one in our calculator. We're going to subtract some complex numbers. I want to do 9 plus 8i minus 5 plus 3i. So you've got to do that. You got to plug it in exactly how you see it here, with the parentheses. So 9 plus 8i minus 5 plus 3i. And we get 4 plus 5i. And that should make sense because if we were combining like terms, 9 minus 5 would be a 4. 8i minus 3i would be a plus 5i. All right, and we'll skip this one. You can try on your own right now if you want. Actually, here, I'll make that one an embedded question for you. All right, how do we multiply? So here's how we do it by hand. We are going to FOIL this. So you go first, outside, inside, last. Now, something special is going to happen when you multiply those last ones. But let's get through the first, outside, inside first. So 4 times 6, that becomes a 24. 4 times a negative 3i becomes a minus 12i. 5i times 6 becomes a plus 30i. And then here's our last. 5i times a negative 3i becomes a negative 15i squared. Multiply the coefficients, multiply the i's. I times I becomes I squared. But what do we know about I squared? I squared is equal to negative 1. That's the definition of I. It is the square root of negative 1. So when you square it, you get negative 1. So right here, we could replace this I squared with a negative 1. And that would make this whole term just a positive 15. So now I'd have 24. I can combine like terms here. Negative 12i plus 30i becomes an 18i, so plus 18i plus 15. And then bring our real numbers together and write them at the beginning. So the 24 and the 15 come together, becoming 39 plus 18i. All right, so one thing you'll realize is that if we were multiplying like binomials with actual variables, it would keep growing in degree. We would get a quadratic. If we bring another one in, we'd get a cubic. Complex numbers never grow past just being complex numbers, just a real and imaginary part. It's because every time we get an I squared, we can simplify it back down to being a negative 1. All right, we'll expand this next one. We'll do the calculator for this, and you can try it. Oh, whoops, I'll make that to stop. You can try it maybe by hand, but here I want to do 2 plus 3i squared. So in parentheses, 2 plus 3i, square that, and I get negative 5 plus 12i. Negative 5 plus 12i. All right, here's another one. I'll do this as another embedded question for you to try on your own. Here's one more, and let's do this one out by hand, just to show that it doesn't ever get bigger than a single complex number. So 2 minus 3i to the fourth. I'm going to do 2 minus 3i times 2 minus 3i, dot, 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 because I've got 2 more of those, but I'm just going to distribute the first 2. So first, outside, inside, last, I get 4 minus 6i minus 6i. And here, let's see if we can do this in our head. Negative 3i times negative 3i would become a positive 9i squared, but the I squared would be a negative 1, so that would become a minus 9. So now this would become a negative 5 minus 12i. And because it's to the power of 4, I would have done this again over here, got another negative 5 minus 12i. Let's FOIL these out. First outside, inside, last. 25 plus 60i plus 60i. Negative 12 times negative 12 is a 144, but then the I squared makes it a minus 144. And we combine these up. 25 minus 144 is negative 119 plus 120i. Should we see if that's what we get in the calculator? 2 minus 3i to the power of 4. And there we go, negative 119 plus 120i. All right, this is something the calculator isn't quite as good at, is dealing with fractions. It can still do it, but sometimes it'll give you a really funky looking answer because it'll use decimals instead of fractions, and then you can convert it back to fractions, but even then it can end up looking a little bit funky. So this is a good one to know how to do by hand. If there's an I on the bottom, but this is just a single term, so if this is a monomial, yeah, I gotta rewrite that. If this is a monomial, multiply by I over I. So I'm going to take this, multiply it by I over I. And the reason we don't consider this to be fully simplified until you've got the bottom of the fraction to be a single integer. That's just sort of the rule in math, is you want the simplest thing you're dividing by. And if you think about like long division, it's much easier if you've got a really simple divisor than a more simplified numerator. So that's why we want to do this. All right, when I multiply by I over I, this I has to get distributed. So it'll become 9i plus 4i squared on the top, and the bottom will become 5i squared. The I squared is equal to negative 1. So this becomes, right over here, 9i minus 4 over negative 5. And then on the top there, I want to write it with the I at the end. So this becomes negative 4 plus 9i all over negative 5. And now technically I also don't want a negative in the bottom. So I'm going to flip the sign on everything and write this as 4 minus 9i all over 5. And that is considered to be more simplified than this. All right. So now what if it's a full complex number, not just something that's a monomial in the bottom? How do we get rid of I here? Well, what won't work is to multiply by I over I, because it would get rid of this I, but then this would pick up an I, and we would still have the imaginary number in the bottom. So what we're going to do is we're going to multiply by something called the complex conjugate. To form a complex conjugate is very easy. All you do is just flip the middle operator. So this is a complex conjugate. Complex because it's a complex number. Conjugate because it is the same binomial with the middle operator flipped. We use conjugates all the time in math, not just for complex numbers. All right, but whatever you do to the bottom, you've got to do to the top. So you got to do a 1 minus 5i on the top as well. And put a set of parentheses around the top just so that you do this distribution correctly, and then you're just going to FOIL the top and the bottom. So I'm going to FOIL, and I'm going to FOIL. All right, what's it going to look like after I FOIL? Let's do the top first. So first we get an 8. Outside we get a minus 40i. Inside we get a plus 4i. And last we get a minus 20i squared. All over first is a 1. Outside is a minus 5i. Inside is a plus 5i. And last is a minus 25i squared. This is the power of the conjugate right here. It's that these middle terms are exactly opposite and can cancel out. And then because this I squared becomes a negative 1, you'll notice there's no more i's on the bottom here. So let's simplify this. Now we've got 8 minus 36i. This I squared becomes a negative 1, so this becomes a plus 20. All over 1 plus 25. And combine like terms one more time, and I get 28 minus 36i all over 26. So now there's no I in the denominator anymore, and now you might also notice we can keep simplifying because everything's even. Let's divide everything by 2. And we get 14 minus 18i all over 13. All right, and this is one that the calculator is pretty bad at. Let's just see what it would have given us. 8 plus 4i over 1 plus 5i. 8 plus 4i all over 1 plus 5i. See if the calculator can simplify this. And it gives us these really long decimals. Now we could take that and hit math, enter, enter to turn it back into fractions. And we do get something that looks pretty similar to this. It does distribute the division of the 13, which we don't necessarily want. We'd rather have it like this. So your calculator can do it, but it is useful to know how conjugates work and being able to do this by hand. Again, you might have to do this on the non-calculator portion of a test too sometime. So here's just a table summarizing complex conjugates. All you have to do to find it is flip that middle operator. So 2 plus I becomes 2 minus I. 6 minus 4i becomes 6 plus 4i. One thing to recognize about conjugates is that conjugates are always conjugates of each other. It's a kind of cyclical pattern here. I'll put a few more for you to try here. We'll call that the end of this lecture video. Have a good rest of your day.